I'm James Kane, visiting professor at University of Pittsburgh School of Medicine. I'm going to be talking to you today about neuromuscular diseases and disorders. This talk is made up directly from the keywords as listed in the American Board of Anesthesiology in preparation for part 1 of the written examination. I have nothing to disclose financially for this discussion. Neuromuscular diseases and disorders are important in the world of anesthesiology. In this first part of our discussion, we're going to talk about the physiology of neuromuscular transmission, and then the second part will be about the anatomy of the neuromuscular junction. The physiology of the neuromuscular transmission can be divided into prejunctional and postjunctional events. Prejunctional being the events that happen at the neuron level and the postjunctional parts being those at the muscle. In the prejunctional events, they can also be then further divided into the acetylcholine synthesis and release, and then the modulation by nicotinic and muscarinic prejunctional receptors. Acetylcholine is the neurochemical transmitter that makes this whole engine drive. It is formed in the nerve cell by combining acetate with choline, using acetyl coenzyme A to form acetylcholine. The acetylcholine is then taken up by vesicles. These vesicles contain the neurotransmitter acetylcholine, and those vesicles, once the depolarization of the nerve occurs, will eventually be released by exocytosis into the synaptic junction. As this occurs, you will then have the neurotransmitter taken up by the acetylcholine receptors on the muscle cell. This whole process is actually modulated by nicotinic and muscarinic prejunctional receptors. The acetylcholine receptors can be divided into nicotinic receptors and muscarinic receptors. The major difference between the two is that the nicotinic prejunctional receptors are a direct channel. That is, when they are stimulated, they will allow the influx of sodium into the cell to depolarize the membrane. Muscarinic receptors, though, on the other hand, are a much different category of receptors. They function through intracellular G proteins as a secondary messenger. In this particular circumstance, the release of acetylcholine by exocytosis is augmented further by these presynaptic prejunctional receptors that are the nicotinic acetylcholine receptors. That is, the more acetylcholine is released, the more acetylcholine will be released, as there's an augmentation of the release by the nicotinic acetylcholine receptors. The muscarinic receptors, on the other hand, function in a different fashion. They are inhibitory, and it's the balance between the two of these that has the overall modulation of output of the acetylcholine by the neuron. This is important in the anesthesiology world as well, because our non-depolarizing muscle blockers will hit not just the nicotinic acetylcholine receptors on the muscle, but also these prejunctional ones as well. And it's believed that this plays a role in why, with non-depolarizing muscle blockade, you'll see a fade occur when you're using a train of 4 monitor. So what type of postjunctional events occur to make the muscles have this contraction? Acetylcholine binds to the acetylcholine receptors, and there's an ion flow through the acetylcholine receptor. So this is a look at the acetylcholine receptor in the in electron micrography. If you were able to draw a schematic of it, what you would see would be the structure of the acetylcholine receptors having two receptors effectively that will be able to accept acetylcholine. And it's only when these two acetylcholine receptors are filled that you'll have an opening of the sodium channel. So this is a chemically mediated ion channel that's opened once the acetylcholine neurotransmitter is released from the axon into the synaptic junction and then is taken up by these receptors. This sodium flow through the receptor is a two-part process. Initially, there is a simple flow as there's a high amount of sodium in an extracellular space and a low amount in the intracellular space. This ratio is kept in place by the active sodium-potassium pump, in which there are 3 sodiums pumped out of the cell for every 2 potassiums that come in, creating a relative negative charge of the intracellular space. As this sodium channel is opened by the acetylcholine, what you'll see is a rapid influx of sodium that occurs, causing there to be a change in the intracellular membrane charge from minus 70 milliamps to minus 55 millivolts or so. And when you get to that level, there's a second ligand-gated, voltage-gated opening that occurs that then causes a further massive influx of sodium into the cell and the rapid upswing in the membrane potential and the rapid intracellular increase in charge, so that effectively the intracellular space becomes more positive than the extracellular space. Once this gets to the range of roughly 70 or so millivolts externally, this channel will close, the sodium will not flow in anymore, and a separate potassium channel opens, which then causes the repolarization of the cell. This repolarization of the cell actually overshoots and goes even more negative than it was at the beginning. And there's an idea that this is in order so that there is effectively a rest period, if you will, or no ability for there to be a reverse charge that occurs in either the nerve or the muscle. So again, this looks at those same things again. We have now the receptor that undergoes the conformational change. The channels are open. The sodium flows inward in a very, very rapid fashion, further speeding along once the voltage gate is opened, and then the potassium sort of quenches the process by repolarizing the cell. Moving on, we'll look at the anatomy of the neuromuscular junction. So we've seen a little bit of the physiology of it. Now we'll look at what the different components really are. You have the motor neurons, the neuronal transport system, and the synaptic vesicles, which we've talked a little bit about already. The motor neurons can innervate more than one muscle fiber. In fact, they typically do. On the other hand, muscle fibers, except for extraocular muscles, are nearly all innervated by only a single nerve. But these several muscle fibers that are innervated by the same nerve are referred to as a muscle unit. What we're going to concentrate on is the neuromuscular junction down here And that's how the neuromuscular, how the nerve charge passes on to the muscle. The neuronal transport system is a system of microtubules and multivesicle bodies that are able to bring different nutrients and the such down in all along the axon, all the way down to the terminal axon end. This also is covered by a myelin sheath. And this myelin sheath has little gaps that are known as the nodes of Ranvier. This myelin sheath is critical as you progress along your training, and you'll learn about some disease processes that affect them. This myelin sheath allows the marked increase in speed of time of transport of the neuronal signals to the end axon. You looked at this a little bit in the earlier slides. This has the synaptic vesicles in it. So again, the acetylcholine is made from choline and acetate. And this acetylcholine then is stored in synaptic vesicles. As the axon end is depolarized, there is a calcium channel that is opened, the voltage-gated calcium channel. The voltage-gated calcium channel pours in calcium, and when the calcium comes in contact with these synaptic vesicles, it allows this to become in contact with the membrane and exocytosis occurring, allowing the acetylcholine to be discharged from the synaptic vesicles into the junctional space. Once this acetylcholine goes into this space, how does this actually end as far as the acetylcholine? Where does it go? Well, simple diffusion takes care of some of this, diffuses away from the cholinergic receptor, but also the excess acetylcholine that is here in the junctional space is broken down by acetylcholine esterase into choline and acetate, with the choline then being actively taken up and transformed back again into the acetylcholine that we're so interested in here. This again is electron micrography, looking at this synaptic vesicles in an actual axon, and in this one a dendrite rather than a muscle cell. This shows you this quanta of vesicles, with each of these vesicles having multiple acetylcholine in them, and the ability for this to then come very close in contact to its partner. And when these vesicles are opened and released by exocytosis, the acetylcholine comes pouring out again. So what happens on postjunctional receptors? Postjunctional receptors, here in this circumstance, we're considering the muscle cells. The muscle cells are interesting because they are they're really the only cells in our body that have multiple nuclei, all capable of producing these different components of the muscle, and all capable of taking care of the energy of the muscle cell. The muscle cell itself, where the real action takes place, is right here at the junction of the axon and the muscle. What you'll see when you look at this closely is the nerve coming down into contact or near contact with the muscle. There's a myelin sheath that's all around the nerve and wraps it and coats it and keeps it insulated basically the entire way down from its nucleus. And the Schwann cells at the bottom play a similar role to what the myelin did up above. In this nerve terminal, you again see these vesicles, and then you see that in very close proximity is the muscle. These muscles have clefts, and in these primary and secondary clefts, you will find the sodium channels. Sodium channels are going to be activated again by the acetylcholine, and the whole process that we talked about over the course of this lecture will proceed. Once these sodium channels are changed and the muscle cell is depolarized, calcium in this circumstance comes pouring in and interacts with the actin and myosin complex to facilitate the contraction of the muscle cell. So again, here is a nice little look at the acetylcholine receptor in a very close-up view. And this is where the acetylcholine binding sites are going to be on the muscle. So this is as if we've zoomed right in on that level of the cell membrane of the muscle. Again, on the muscle side, you've got the same type of voltage-gated channels. You've got voltage-gated no sodium channels, and we also have voltage-gated calcium channels. As the depolarization occurs, these channels are going to flood open. Sodium will come pouring in, but also in the end, you're going to have the calcium coming in as well. And the calcium is where the contraction of the muscle is going to be precipitated. I want to leave you with some words of Professor Stephen Hawking. You may have recognized him as the gentleman in the very beginning of the presentation on his wedding day. He suffers from ALS, a disease of the neuromuscular process, and still is able to shoot for the stars. In his words, remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious, and however difficult life may seem, there is always something you can do and succeed at. It matters that you just don't give up. Thank you for your time, and good luck on your examinations. Thank you.